Welcome to the BAA meeting of 31st of March 2021, which we are again holding as a webinar due to coronavirus restrictions. This is being held on Zoom and live streamed to YouTube. The webinar is being recorded and will be available to watch on our YouTube channel a few hours after the meeting. You can ask questions by typing them into the Q&A at the bottom on Zoom or in the comments on YouTube, and we'll answer them at the end of the presentation. It's my pleasure to hand over to Alan Lorraine, the President of the BAA.
Thank you very much indeed, Andy, and welcome to everybody, both BAA members and non-members watching on Zoom or on YouTube as well. So just from an admin perspective, just before we start the main meeting, in our spring meeting in each year, normally we would have a special general meeting to confirm the amount of the subscriptions for the forthcoming year. In view of the pandemic, we can't meet in person at the Institute of Physics, but in addition to that, we feel it inappropriate to be raising the subscriptions this year, and so the purpose of that special general meeting is no longer there. So the subscriptions will remain the same for next year as they were this year, and then we can move on to the meeting in full today. So the slide is on your screen already. I just want to give you a bit of a background. Professor Dimitra Grigopoulou from the University of Oxford, originally from Greece, where she studied physics, and she then came over to the UK to study for her PhD in 2003. Sorry, no, she came over in 1990. She studied her PhD at Queen Mary's College at the University of London before moving over to Germany for a spell at the Max Planck Institute of Extraterrestrial Physics. You need a long business card for that one. She returned to the UK in 2003 to Oxford University, where she was initially a research lecturer, but is now working as a professor of astrophysics. And so we're delighted to have her talking to us this evening. So tonight, Dimitra is talking about lighthouses in the universe, and as on the screen, the tale of ultra-luminous infrared galaxies. These were discovered back in the late 1980s, and they are one of the most prolific sources of star making in the whole universe. And fortunately, they're also relatively nearby, which gives scientists the opportunity to observe them and discover their details as well. So without further ado, if I can pass him over to Dimitra.
Thank you, Alan. Good evening, everybody. It's a pleasure to give this talk, albeit via Zoom. Apologies for that, but that's the weird kind of life we are all leading these days in front of the screen. Anyway, so I'm delighted to give this talk. Ultraluminous infrared galaxies are a topic that I have researched throughout my career as an astronomer. And I, even to this very day, there is still enough to be discovered about these galaxies that, you know, my interest in them and that of my colleagues is great. I should like to say for this talk this afternoon, this evening, the work that I'm going to present is from our group and my collaborators. So I would like to thank all the people back in Oxford and my collaborators worldwide for, you know, working on proposals to help us get the data that I will be talking about today. So this is right. This is the outline of what I will be talking about. So I will start with some definitions, just some terminology that I will be using throughout the talk. So it's good to sort of get this out at the start. Then I will get into the main talk about the properties of ultraluminous infrared galaxies, why we call them the lighthouses of the universe. I will come a little bit into their some of their the characteristics of their complex nature, and how we use them, how we use the observations from this class of objects to understand better galaxy evolution in the universe from the early universe, early time, to the present day, basically. So galaxies are very important because they're the fundamental blocks of the universe. Some are simple in morphology, while others are more complex in structure. One of the first steps towards a coherent theory of galaxy evolution was taken by Edwin Hubble in 1920s by this classification scheme, which I'm sure you're all familiar with, whereby Edwin Hubble classified galaxies based on their morphological appearance. This scheme, also known as the Hubble tuning fork because of its appearance, is nowadays considered too simple. And this is sort of today's version of the Hubble tuning fork diagram. We know that the morphology of galaxies is a bit more complex and more varied than what Hubble sort of originally described back in the early 1920s. However, the principle sort of still remains. There are spiral galaxies, there are barred galaxies, intermediate in between, and the elliptical galaxies. So we still use the nomenclature that was first invented by Hubble, although, as I said, this is now considered a bit too simplistic. For today's talk, I will focus on this particular class of galaxies, the irregular galaxies, which we've all sort of clumped them and parked them on the side because we couldn't easily fit them in any of the other classification, any of the other sort of boxes, as it were. These are galaxies that don't have a very specific shape. They can show a lot of arms and a lot of signs of interaction, tidal tails, tidal arms, or even they can be very small, tiny, like dwarf galaxies. So all of this belong to this category of irregular galaxies. The galaxies I will be talking about, the ultraluminous galaxies, are in fact, as you can see, irregular galaxies because of their appearance. You know, you can't call them a spiral and you can't call them a barred elliptical or an elliptical or a barred spiral. They are the result of interactions, galaxy interactions and mergers, so their morphology is very irregular. So before I proceed, as I said, I think I will just sort of go through some definitions that I will be using in my talk. And I do apologize in advance if this is, you're already familiar with that, but I just thought it's sort of better to set the stage, as it were. So on the left here is a sketch of Sir William Herschel, who is sort of considered the father of infrared light. And in fact, we had a satellite named in his honor, where in the year 1800, thanks to his experiment, we came to know that the light light from the sun consists of a range of colors rather than just one color. And Sir William made this discovery with a very simple experiment whereby he let the light from the sun pass through a prism. Now, this prism divided the light in a rainbow of colors, which we call the spectrum. The spectrum contains all the lights, all the colors that make up the sunlight. And Herschel was interested in actually measuring the amount of heat that you could get in each color. And to do this, he used thermometers with blackened bulbs, and he measured the temperature in the different colors of the spectrum. He noticed that the temperature, for instance, here in the red, was higher than the temperature in the blue. Then he placed the thermometer sort of to the far away from the red, sort of in this kind of area, and he noticed that the temperature was even higher. And through these measurements, Herschel realized that there must be another type of light which we cannot see in this region, but and this is what he called infrared, so this was further than the red. So infrared light is a form of light that we cannot see with our eyes, but we can sense it. We can sense it on our skin as heat. So, and when I talk about infrared, I talk about sort of in terms of wavelength, anything from about 20, 30 microns to 200 microns, sort of that area. Then we go into the far infrared, or in terms of frequency, around 10 to the 12 hertz, so about 1 gigahertz and so on, and about a temperature of that could correspond to a temperature of about 100 K. Now, the other thing that I would be referring to very often is the luminosity, luminosity for the ULEX, and I will always refer to the luminosity in terms of the solar luminosity, which is, as it says there, 3.8 times 10 to the 26 watts. Just to place this into context, an LED, this corresponds to 3.7 about times 10 to the 28 lumens. And to put this into sort of everyday life context, a bulb, an LED bulb that we have at home, a 25 watts LED bulb, is about 1500 lumen. So you can sort of see, make the analogies there. Now, ultraluminous infrared galaxies are 100 billion times the luminosity of the sun, so 10 to the 12 solar luminosity. So we're already getting into the 10 to the 12th kind of regime. And again, I will be talking about their mass, mostly about the mass of their molecular gas. And I will expressing that in terms of solar mass luminosity, solar mass, which is 2 times 10 to the 30 kilograms. Now, ultraluminous infrared galaxies are found both locally, but also further away. Most of my talk, I will be talking about the things that are nearby, local, as I say. Although local is not as local as, for instance, the Andromedas or even the Magellanic Clouds. It's a little bit further than that. So the nearest member of the ultraluminous infrared galaxies group, sample, not group, sample, is about 250,000 light years away in the constellation of Serpens, and that's ARP 220, in honor of W. Arp, an astronomer who did a lot on the classification of galaxies as well. So this was just as a means of sort of setting out some sort of conventions and some units that I will be using throughout my talk. And I should say here, I should point out that I will be using, sometimes I will call them ULIRGs, which is the acronym for ultraluminous infrared galaxies, which is how we call them in our everyday today sort of work life, or IR luminous galaxies. And I should stress here that the IR is important because these galaxies, as Alan said in the beginning, they were discovered sort of in the 1983. That's when IRAS, the first satellite, flew. And they were discovered particularly because they are luminous in the infrared. Now, what can cause that is the following. So the light from, when we look at the galaxy, the light that we see from the galaxy is mostly the light from the stars, that the galaxy is actually primarily the light of the stars. And it's mostly a blue color, right? Because young stars, O and B type stars, will emit strongly in the ultraviolet and blue, mostly in the blue color. However, if you happen to have a lot of dust intrinsic in the galaxy, that we are referring to, in the ultraluminous galaxies in this case. And what happens is that the light from the stars is being absorbed by the dust and reprocessed and re-emitted at longer wavelengths in the infrared. So in some sense, again, we see the light from the stars, but reprocessed. And this is the characteristic of these galaxies, is that they contain enormous amounts of dust. And therefore, the majority of the light from the stars is shifted to longer wavelengths. And that's why we see them very strongly. They shine very brightly at infrared wavelengths. So I just sort of wanted to, again, to clarify this, why we study these galaxies in the infrared. So how and when they were discovered. So as I mentioned already, the first satellite that gave us sort of a full picture of these galaxies was the Infrared Astronomical Satellite in 1983. And that was the first satellite to map the sky in infrared wavelengths. So IRAS carried out surveys at 12, 25, 60, and 100 microns. All of the sky. It surveyed the sky twice. Following that, we had, so IRAS was primarily a NASA mission with contributions from the UK and the Netherlands. In 1995, we have the second satellite in the infrared. This was the European Space Agency's achievement, the Infrared Space Observatory, where we learned an awful lot about Ulrichs. They formed a key part of the observations that were carried out. Then in 2003, we had Spitzer, NASA's Spitzer satellite. And in 2009, we had the cornerstone mission from the European Space Agency, Herschel, in honor of Sir William Herschel. From there onwards, we turned to the ground with a revolutionary and still amazing sort of radio telescope, the Atacama Large Millimeter Array from 2012 onwards. Next year, we are all very excited that we'll see the launch of the James Webb Space Telescope in 2021 in October, a bit more over a year from now. And in 2026, we're going to have the Extreme European Large Telescope, the ELT, where again, we are hoping for more great strides into the research of Ulrichs. You probably noticed that I started off with this infrared telescopes, and now I'm going sort of more in the radio and then in the mid-infrared and in the optical. So I think this is sort of, so going to ALMA, which is a submillimeter telescope, allows us to study another very important constituent of these galaxies, which is the dust, the gas and the dust, because as you will see, these objects have an awful lot of gas and dust in their systems. Likewise, for the JWST, which goes into the mid-infrared, there are a lot of signatures from the dust, but also optical lines, which are still accessible, although we have to make corrections for the effect of the dust and all of this, and so on. So this is how they were discovered from the 1983. Today we know about of the order of 200 to 300 galaxies, ultraluminous infrared galaxies. Actually, I forgot to mention here that for a galaxy to be called ultraluminous, it has to have a luminosity more than 10 to the 12 solar luminosities. Now, this is a little bit of a convention. It might be 10 to the 12, or it might be slightly less, but we know that anything that is sort of 10 to the 11 solar luminosities has different characteristics. So this luminosity basically relates with a specific set of objects, which, as you will see, have have some special characteristics. So what are these? First of all, they're ultraluminous infrared galaxies. They're extremely rare locally. As I said, there are only 200 to 300 known. But we know now, with all of these missions that we have had over the years, that their numbers increase with look-back time. So as we go to more distant objects, higher redshift, earlier in the universe, we know from the missions that we have had that they were a lot more common at earlier times. The second characteristic of ultraluminous infrared galaxies locally is that they're nearly always mergers. And I will stress this time and again, and this is what I was saying earlier, that to reach these luminosities, you more likely than not, locally, you have to have a merger. And this, as I will explain, relates to the characteristics that we see in these galaxies. They're predominantly powered by star formation. So the light, or what hits the dust and they emit in the infrared, is the light from the stars. And they do experience very intense star formation. But we also know that half of them, at least half of them, contain a detectable black hole. And as you know, black holes locally, we call them active galactic nuclei, which is, again, it's more or less of a convention. But that means sort of a medium-sized kind of black hole. So not a very powerful one that will make them a quasar, but a significant one that can be detected with the instruments that we have in our availability these days. So where we study ULIRCs, I guess the most important thing is that locally, they are the only object that they allow us to track this process of galaxy interaction and merging. In the universe, we know that merging is actually a process that happens very, very often. Very often we have a collision of two galaxies. And in the case of ULIRCs, this is a collision of two massive gas-rich galaxies. And the nice thing is that, as I showed in the picture here, because we can see them, we catch them in a variety of stages in their interaction. So we can have systems like this one, where you can still clearly see the two parent nuclei, the two parent galaxies that are involved in the collision, or you can catch them in something like this, where the galaxies have already approached, they have already collided once, they have become a gravitationally bound system, but you can sort of perhaps still see the nuclei, or you can have them like that, which is a merged system already. So they allow us to study how galaxy interaction and merging proceeds. They allow us to study star formation and understand more about how star formation in galaxies proceeds. They have unique properties, and these are for the more sort of weird people like me, where we try to understand how the conditions that will allow star formation to proceed are in a galaxy. And sometimes, as I say here, in the ULIRCs, these conditions are very complex. The nature, the properties of the interstellar medium, I guess, are very complex. And finally, because we know that they existed in the past and we know they exist now, they allow us to understand evolution, how galaxies started from an early age and reached to today. Right, so we talked about their luminosity. I make a great deal out of that. So here is a representation, basically, just to give you a scale of how bright luminous, how luminous these galaxies are. And you can see here, this line, this is a plot of what we call the spectral energy distribution. So we plot the wavelength on the x-axis and luminosity. And this is luminosity scaled in frequency, so to speak, is nu L nu. We could have lambda L lambda. but it's an expression of the luminosity of the object. And as you can see here, for our galaxy, there is a peak here around the optical wavelengths and another one from the dust. And these are probably sort of similar, or maybe the blue peak is actually stronger. But as you go up in luminosity and you reach the Eulerx, the peak that you have in the far infrared is about 10 to 1,000 times brighter than what you have in the blue. And if you take like for like, ultraluminous infrared galaxies are about 100 to 1,000 times brighter in the infrared than our own galaxy, the Milky Way. Okay, so as we said, most of the systems are found in merging and interacting galaxies, and I will sort of demonstrate here why we choose to study and why the study of these systems became of age with infrared facilities. So this is the Sloan Digital Survey image of one of these ultraluminous infrared galaxies. This is R220. And if I were to ask you to point the nucleus of this system, you would probably say that it's somewhere here, sort of where you have this lane of dust. And you would actually be correct, because we know that the nucleus of this galaxy is sort of around there. But the interesting thing is that there is not one, but two nuclei hidden behind this screen of dust. And what is even more exciting is that if you look close up, these two systems, although you cannot see them here, they are counter-rotating, these two nuclei. And although the orientation is not right, this is the west nucleus, this is the east nucleus. And the two bubbles, the blue and the red bubble that come out of the west nucleus, they're actually outflows. So there is gas that is coming out above and below the plane of the galaxy. And we think that this is either wind, that this is blown out from an emerging black hole in one of the two nuclei, or it could be winds due to star formation, that as the gas is being basically stirred up after the interaction, a lot of the gas sort of is blown above and below the plane of the galaxy. So this is an image that was taken with ALMA last year by a collaborator, and I think it makes very well the case as to why we actually need to study these systems with something that is capable, with facilities that are capable of peering through the dust. And what we find actually inside them is, in most cases, rather surprising. Okay, so I talked about ultraluminous infrared galaxies found in merging systems and interacting systems. And I thought it is actually quite nice to sort of see what is happening when a merger takes place. This is not a real sort of merger. It's a simulation, but this is very close to what we think is happening with Eulerx. What you will see here is what happens to the stars when two galaxies collide. So in a minute, you will see the two galaxies coming together and in some random sort of plane. And this is the first encounter, as we see. So as you see, after the encounter, you see all of these blue bubbles coming up. And this is formation of new stars. So the gas, as it was sort of violently brought together, it was compressed, collapsed, and gave rise to star formation. So this is what we think is actually happening. And if you look carefully at that and compare like for like the images that I was showing earlier of these ultraluminous galaxies, you can actually catch snapshots from this process and compare them to what we see. Now, the merger took place, and after all of these violent events, a new galaxy. We have a new galaxy, the merged galaxy appear. How do we know that this is merged? Well, you can actually see these very faint wisps of gas and sort of runaway stars, as it were, here. And this is the tidal tails. And this is a very telltale sign that an interaction has taken place. Now, I have another simulation here where I show this is a simulation of what happens in the gas. And it's not as spectacular, of course, because you don't have this blue bubbles coming up. But it sort of gives you, again, a similar thing. But here we follow the gas particles. What is happening, you can sort of see the colors from the two galaxies that take place in the merger, in the interaction, how the galaxy basically mixes, how the gas, mixes up, and after the end of the merger, you sort of can't tell what is what. Okay, I talked about ultraluminous infrared galaxies being predominantly powered by star formation. And I also showed you via the simulation how these stars are being produced, star formation is being initiated from the compression of the gas as a result of the interaction. But I also said that we know that there probably are black holes in the centers of the galaxies. How do we know this? Well, by plots like this one, by measurements like this ones, where we look, I mean, there are various ways of detecting black holes, but this is one that we favor in this particular sample of galaxies. And this is the oxygen 4 line. This is a line in the mid-infrared. And when you do get this line in your spectrum, it's because it has a very high ionization potential, you can only get this line from the narrow line region of a black hole, of an active galactic nucleus. So this is what I plot in the y-axis, and in the x-axis, I have this PAH, as I call, which stands for polyaromatic, polycyclic aromatic hydrocarbon, which is a dust feature, which is due to a molecule which actually grows on the dust grains. But we know that we can only get those in the vicinity of stars. So whenever we detect this this feature, we know that there is star formation nearby. So we use it as a proxy for star formation. And what we have plotted here are up here are quasars. Here are a couple of Seyfert galaxies. Then we get our ultraluminous galaxies somewhere halfway. And down here we have the points that correspond to purely star-forming galaxies, not ultraluminous galaxies, but sort of M82 or NGC 253 type of normal star-forming galaxies, and not of the luminosity that ULEX have. So through plots like this, through measurements like this, we can infer, we have inferred the presence of a black hole. Now, I said earlier as well that there are various ways of detecting a black hole in the galaxy. I'm a spectroscopist and I use spectra in sort of my investigation. So most of the plots that I will show will involve some kind of spectral signature. Okay, so this is how we detect a black hole, or we detect signatures of star formation from these galaxies. But how do we actually imagine these systems to be in reality? So what I'm going to show here in this view graph are the sort of the best theory of how, the best model of how we actually imagine these systems to sort of appear, how how a model for them, what a model for them looks like. So we start with a nucleus, which is very dusty. And this is the characteristic of Eulerx. Every view graph, I have to say this, it's dusty, and there's more dust and gas, because dust and gas go together. So there's a very dusty nucleus, which we can't easily see. We need, instruments like ALMA to be able to see through this screen of dust. And often there is a galaxy disk around it. Now, what is inside there is interesting. So you can either have an AGN, a black hole basically, and a clumpy torus around it. And this would be a system that is mostly powered by an AGN, or you can have an AGN and a starburst mixture, where again you have the same kind of dust cell, spherical or axisymmetric, and in the middle you have both a black hole but star formation. And this is why Eulerx are great, because you can study the symbiosis of these two phenomena, black hole on one hand, star formation on the other, and actually watch in real time the competition for gas, right? Because stars need gas to, they need gas, they form out of gas, out of molecular clouds. But the black hole also needs gas to feed itself. So it's a very interesting interplay. Or you can have, again, the same structure, a spherical axisymmetric dust cell with only stars now in the middle. Okay, so, and we don't sort of know whether this this dusty nucleus also is completely sealed from our view. So it has sort of a top and a bottom dust cell. We do think actually that there are systems out there that they are completely opaque and there is no line of sight where some of the luminosity, some of the light from the very, very center comes out. They are so very deeply embedded. It is really remarkable. Right, so this is what we think Eulerx look like. But so far, I talked about interactions. I talked about how we measure the star formation. But there is another sort of material, another constituent that we need for star formation, and that is molecular gas. Right, so here what I have plotted is in the x-axis, the redshift, so how distant the galaxy is from us. And in this y-axis, I have the star formation efficiency, which is, as the word says, is the galaxy's efficiency in forming stars. And what we have compared here, so up here are these are the Eulerx, the local Eulerx that we have been talking about. And down here are some Eulerx, but at earlier times, so younger Eulerx, more slightly more distant ones, not very. And you can see basically that the local Eulerx that I have been talking about, they have a higher efficiency. So they use their molecular gas efficiently, more efficiently to form stars. And they have quite a lot. They have about 10 to the 10 solar masses in terms of molecular gas, molecular hydrogen. The other thing that we have realized for this Eulerx is that the gas is very dense and concentrated in the centers. And I show here again a picture of gas in this is molecular gas. And here in the red, you can see this is a gas that is traced by HCN, which is a molecule that traces very dense gas, which is the gas that really is able to form stars, because not all gas in a galaxy is in such a condition. The conditions in the gas are not right for it to form stars. And I will come back to this point again later on. But for now, Eulerx have a lot of gas and they have this ability of burning it basically to form stars. These are some very nice, I couldn't resist not showing this, and apologies if it looks very complicated, but what I would like you to take away from this plot are these red areas, which denote the regions where we have quite a lot of gas, basically. And these are measurements from ALMA. With exquisite resolution, we can actually, ALMA allows us to sort of look down to 400 to 500 parsecs at the distance. So this is 0.3 to 0.4 arc seconds resolution, as we say. And this is another sort of very nice confirmation of what we thought, that the molecular gas reservoir of the ULERGs is indeed very, very large. But this is all very nice, and I talked about a lot of properties that we understand about the ULERGs, and we use them to build a concise picture of what we think is happening in these galaxies. But there are some properties which are still puzzling us. And I'm going to talk now a little bit about here about what is called the so-called far-infrared line deficit. So the far-infrared spectral lines of elements like carbon, oxygen, and nitrogen, either in their neutral form, so neutral carbon, oxygen, or nitrogen, or ionized, where you take an electron out. They're very important lines to study these lines, because they allow us to track how the molecular clouds in a galaxy start to collapse. As I said earlier, you may have, you need, molecular gas, you need molecular clouds to form stars, but not all clouds are capable of forming stars. You need to let the cloud cool, fragment, and that is how you start forming stars. So this is a very sort of naive sketch that I thought I should just put together, where you have a parent cloud, molecular cloud, and then you detect carbon, nitrogen, oxygen out of that, and then you know that this cloud is on its way to start the formation of stars. I mean, this is a very simplified version, and the problem of cloud collapse and star formation is supremely complex. And as I said, I should apologize for just making it into a simple cartoon, because it's not. But I just wanted to sort of show just the basic concept, basically, that the cloud has to collapse, to cool, collapse, and these lines enable the cloud to collapse, so they take heat out of the cloud. Now, what we realized about these ULERGs, and I will talk about this R220, which is the archetypical galaxy, is that they behave very weirdly when it comes to these cooling lines, the carbon, oxygen, and nitrogen. So these are some spectra. As I said, I do work with a lot of spectra from the Herschel satellite. And here we have compared M82, which is a classical star-forming galaxy, local, NGC 253, 4945. And here we go in the ultraluminous galaxy R220. And you would notice that this line that I have circled here, that is quite strong. And then we reach up to R220 and it's barely there. This is the carbon-2 line at 1558 microns. And what I would like you to remember out of that is, for us, is a very crucial line, because it gives us an indication, is the strongest line in the far infrared spectrum. And when we see this line, we know that the clouds, the molecular clouds in the galaxy, in that galaxy, and in our galaxy actually, could be on their way to forming stars, because it's a cooling line. So it allows the gas to cool, fragment, collapse, and form stars. So if we now plot the strength of this line as a function of far infrared luminosity, these are some normal galaxies, and this is where the ULERGs are. So this is what we call the carbon deficit. Another way to plot, to represent this fact, is this plot, where here we plot the luminosity in carbon-2, which is the ability of gas to cool as a function of infrared luminosity. And as you can see, we're looking at local, just normal galaxies, not ULIRCs. They follow this line. We look at galaxies between 0.2 to 0.6. They follow the line. We look at galaxies, more distant ones. They follow this line, but local ULIRCs do not. And this is a puzzle that has been around since sort of the early 2000s, and we still don't have a good answer as to why this is happening in the ULIRCs. And this is what is responsible for the line deficit. This far infrared optical depth. Remember, I talked to you about this cocoon, this dusty cell. Maybe this dusty cell is just too deep and we can't see the line. Maybe the regions of the ULIRCs are very small, so there is less carbon-2, the regions where they form stars, where this collapse happens. This is still an open problem for the ULIRCs. We are still sort of trying to understand why this particular property of these systems is so unusual. So I talked about the ULIRCs nearby. In the last sort of 5-10 minutes or so, I want to sort of briefly talk about what happens in the ULIRCs further out. What I show in this plot is a plot which shows how the stars are produced, how many stars are produced by each type of galaxy. So you can see here the LIRCs, luminous infrared galaxies. And as I said, these galaxies are about 10 to the 11 solar luminosities, luminous, and these are the ULIRCs. And you can see that the ULIRCs sort of come and become important with look-back time, sort of with galaxies in the early universe. Do we know, are there any ULIRCs in earlier times? Well, yes, there are. Thanks to Herschel, which surveyed large patches of sky, we now know that there are a lot of ULIRCs out there in the distant universe. And here are some of the images of these things. Obviously, the resolution, the ability for us to see the details is not the same as the ones we have locally, because of course they're further out, but we can still see. I mean, this looks interesting, intriguing, as does this one. So yes, there are a lot of galaxies, luminous galaxies out there, and in fact, it appears that they were very common in the past. So finishing off, this is a project that I ran in Oxford for a number of years now. So what we have done is that we have taken samples of galaxies at about 9.6 billion years ago. So this is a redshift of 0.4. And we have tried to see morphologically whether these galaxies are mergers like the local ULIRCs or are not. And it's very interesting what we get. So this is a plot of the V over sigma, and we are talking now about measuring the velocity of particles within the galaxy, okay, the velocity dispersion, and we are trying to see if the system is rotationally supported or not. Now, before I move on into more details, let me just quickly, because I thought this is a very nice cartoon that that explains this very nicely, whether we have a rotationally supported system, which you can see on the left, and what happens. So all the stars rotate in the same way, and this would be a rotationally supported system. Or on the right, we have a system which shows velocity dispersion, which means that the stars are moving in all kinds of sort of directions, right? So that system is what we call a pressure supported or a velocity dispersion, where the motion of the stars is basically random. And what happens is that in sort of the thin or thick disk of spiral galaxies, we have, this is what we normally see, this normal rotation, whereas if we have sort of systems like stellar halos at the bulges of spiral galaxies, those ones possess very little or no rotation. And if you have an interaction, you are in this category, basically. So by looking at this velocity, the velocity dispersion, we can actually tell where a system is interacting or is a nice settled disk. We are either rotationally supported or pressure supported. Okay, so with that little explanation, from this sample of ULIRCs, which are at redshift 0.4 or 9.6 billion years ago, we went out and we imaged these systems. We measured their velocity dispersion. And what we can actually find, these are these red crosses here, is that yes, there are systems that are interacting. So the ULIRCs, the local ULIRCs are these green points. But we sort of see that there are systems which are tending, which are actually rotation supported. So as you go back in time, so in the early universe, you sort of start seeing that things were a little bit more settled. Now, we've also done an experiment by going even further back, and we defined a sample with an age of 5.9 billion years ago at redshift 2. And again, we took some images and we tried to look at the same thing. How are these galaxies pressure dominated, so dispersion dominated, or are they actually rotation dominated, rotation supported? And here we find that although we still have a couple of interacting systems, the fraction of interacting systems is actually going down. So it does appear that as you go back in time, you had fewer of these interactions happening. Now, this is bizarre, right? Because these are also ULIRCs and they also support, they also have quite a lot of star formation. So what all of these kind of studies led us to develop, not myself, because I'm not a theorist, but the theorist, is that there are two sort of paths of ways of forming stars in the universe. And what you see here in the top is the starburst path of major mergers, where basically you have the two gas-rich galaxies. As you saw, they interact, they merge, and they form something that looks like a galaxy. That was, again, my attempt of drawing a merged system. Or you can have what we call the smooth accretion, which is what we think is happening for these galaxies at earlier times, where basically you start from a small little bubble, and then you have a slow, steady funneling of gas from the intergalactic medium. And as time passes, this sort of accretion fits the galaxy with enough gas to maintain star formation. Not at the extreme rates that you have with the ULIRCs, where you see these bubbles of blue, the blue stars coming out every so often. It's a more sort of continuous and less episodic star formation. But we think now, I think a lot of research has gone into this, and we think that this is indeed the case, where we can have two pathways of forming stars in the universe, of galaxy evolution. And the local ULIRCs are following this path here, whereas the more distant ones are following a slightly different path. If I'm to put it out in a bit more sort of scientific way, these are the two sequences. So this is the sequence of what we call of starbirth, of which the ULIRCs are part of. And down here is the second sequence of disks, of more normal galaxies, of the rotationally supported galaxies that form stars at a lower pace, but they sustain it for a longer period of time. So I think I'm gonna close this talk here. We'll just putting out my just a few summary points. of why we study ULIRCs. They allow us to study the coevolution, the symbiosis of black holes and star formation. They allow us to understand interactions and mergers of gas-rich galaxies and the birth of stars, both in the early universe and in the recent universe. Finally, ULIRCs help us to better understand our cosmos. So I'm going to stop here and thank you.
Thank you, Dimitra, for a fascinating talk. And we've already been getting some questions come in during the presentation. But just to remind people that if you would like to ask a question, you can use the Q&A at the bottom of the Zoom screen and also look out in YouTube. First question is from Peter Jedick. Is ULIRC ARP 220 a satellite galaxy of the Milky Way?
No, it's quite further out actually. As I said, it's at the 250,000 light years away. In particular, up to 20. They're not as close. They're not in our sort of backyard ULIRCs, as it were. They're a bit further out. We don't have any member of a ULIRC sort of system within a few megaparsecs. None is known to date.
Then from Darryl Dobbs, have they on average got strong magnetic fields, and where there are two nuclei, is there one or two magnetic fields?
That's a very good question, thank you. The answer is probably there are, but that's just what we think exists, because unfortunately detecting magnetic fields in galaxies is a very, very challenging task to do observationally. And although we have observed magnetic fields in our galaxy, in our own galaxy, and we know that they play an important role in star formation, unfortunately, we don't have the ability to measure magnetic fields in external galaxies. There are experiments where we can look at polarized lights and all of these things, but not magnetic fields as such. So the answer is probably there are, if there are two nuclei, but this is just what, you know, we can infer from what we know. We haven't detected anything. We don't have any signal to date. Hopefully with future space missions, we might be able to get a confirmation.
Thank you. Next, we have a question from Roger Dimmock. Why are ULIRCs so dusty? Where does the dust come from?
Another excellent question. Thank you. So dust goes hand in hand with gas in the universe. So you can't have gas without dust and the other way around. So we think because the merging happens between two gas-rich galaxies, there's bound to be dust mixed with the gas. They go hand in hand. And the fact that I've been saying that there is a lot of gas and dust in the nucleus, we think that this sort of funnels in from the interaction. So when you have all of this very violent very violent events happening in the nucleus, that causes gas to sort of funnel in and pile up in the nucleus of the new galaxy. And because gas piles in, dust will pile in as well. So as I said, they just happen to have a lot of, these are the gas, what we call the gas-rich galaxies. Why some of them are gas-rich and some aren't, also has to do with how they have been using their gas. So for instance, nowadays ellipticals, they've used their gas, gone. These galaxies, we catch them in the process of using their gas. So there's still quite a lot of them, if that makes sense. And as I said, when you have gas, you also have dust. And that's sort of, we know this for a fact.
Thank you. And then what may be the final question is from Darryl Dobbs, and he asks, have you ever seen evidence of more than one merger? Or And we've got another one coming in afterwards, so it might not be the last one.
Okay. Sort of two mergers, a merger of a merger, so to speak. So a merged system going with another galaxy, interacting. Well, yes, actually, I should have, I sort of very briefly touched upon that when I said that these ultraluminous galaxies, the ones that are more than luminous, more than 10 to the 12 solar luminosities, they're the result of a merger of two equal mass, more or less gas-rich galaxies. But yes, you can have a merging with the smaller galaxy, a satellite galaxy. And we know this is happening. We don't have evidence because this is a matter of resolution as well. If it's a smaller one coming in, we might not be able to catch it. But we know from people who do simulations of galaxies, very often you can have a merger and then a third system is caught in the gravitational field around this whole system and sort of flies in. We know that this can happen. But we need very powerful telescopes to be able to catch these things. So yeah, they can happen.
Thank you. And then we'll make this the final question, which is from R. Whiting. If there are two ways of forming stars, can you tell which method was used for a given star, or is the end result the same?
The end result is the same. What is different? So the stars won't be different. What is different, though, is when we measure the star formation rate, which is how many stars a galaxy produces in a year. When we talk about star formation rate, we express this in units of per year, solar masses per year. And this is sort of, again, it's a convention that we use, but for ULERICs, we know that they have a higher star formation rate, so they are capable of converting a lot more, of churning out a lot more stars per year than through the other pathway, the sort of the steady, the main sequence way. Those galaxies will have a lower star formation rate per year. The stars will be the same, but it's how many of them galaxies produce.
Thank you, Dimitra, and thank you again for a fascinating talk.
Pleasure.
Hi, Alan.
Hi there, Dimitra. Thank you very much indeed. That was excellent. Really good. Well appreciated.
Thank you. Okay, I'll stop sharing now. If that's okay.
Thank you. Andy, are you ready to?
And Owen, are you good for sharing your screen?
Yeah, we can give it a go.
So if I can just take the opportunity to introduce Owen Zell. Obviously needs no introduction to BAA members. For others of you who may be watching, well known for the Webb Deep Sky Society, regular contributor to Astronomy Now, and the assistant director for the BAA Deep Sky section. So very well respected. I'm sure there'll be lots of deep sky images coming up in the next 20 minutes or so. So over to you, Owen. Thank you very much.
Okay, thank you very much, Alan. So this is my first attempt at this, and we'll see how it goes. So I'm going to start off with looking at the moon, as it says there, everybody's favourite source of light pollution. There's some very nice images, of course, of that coming through. The moon very much controls what we're going to be able to observe, and this graphic sort of gives you an indication of the dark sky over the next month through April, and then similarly we have another one through May, though in many cases, of course, by the time May comes around, it doesn't really matter whether the moon's there or not because it doesn't get dark. So these are the phases of the moon. Obviously, we're coming off full moon a couple of days ago now, and the moon will be coming towards new on around the 14th of April. and then coming back up to full towards the end of it. Similarly, we'll see a not dissimilar approach in May, where new moon is at the middle of the month and we get to full moon again at the end of the month. From the moon's point of view, apart from obviously looking at it, I've checked through the handbook and there don't seem to be any suitable lunar occultations in this period, partly because the skies are brightening and most of the stars that would be bright enough to be seen would be daylight anyway. So of things of interest, most members hopefully will have come across this already. There was a nova discovered in Cassiopeia on the 18th of March, so about 10 days ago or so. The nova has brightened, and we'll have a look at that in a minute. But when we did a search of the position, there appears to be a WA type system called CZEV 3217 at about the location, and this is a binary system. Obviously, until the nova dies down again, we won't be able to see for sure, but that's what it looks like is going forward. Now, the nova itself, this is an image by David Swan, is in a fairly photogenic location, particularly if we're using a wide field instrument. So we have up here the cluster M52 up in Cassiopeia, and then over here the bubble nebula, an emission nebula surrounding an O-type star in that area. And the nova itself is this bright object here, and it is probably not within naked eye visibility, but certainly binoculars should be able to show it up. Unfortunately, the timing suggests that Cassiopeia is going to be low through the northern sky, so the best times for it are probably going to be early evening or early morning as Cassiopeia starts to rise again. This is an image that Nick James took of it. As you can see, it's circled by the little blue circles there, again showing that the nova has brightened quite a lot. The BAA has a large number of spectroscopists now in its armory, and these are two spectra taken with both a more precise instrument by David Boyd and also by Mike Harlow. But the Mike Harlow one is interesting because it shows the emission lines from hydrogen here, and David's spectra also shows some of these emission lines as well. And as the nova has progressed, many of these are starting to show P Cygni type profiles, which is what you would expect from an expanding gas shell. Now, this is the current light curve for this nova. As you can see, there is quite a lot of scatter, but it basically suggests that the nova is around 7.5 and very slowly fading or still in a plateau phase. So if you have a chance to get out and have a look at it, now would be a good time. Obviously the VSS would love to have some estimates as to what it's doing, then we can decide what kind of nova it is and where it's going. It is obviously a classical nova, not a dwarf nova, just from the outburst magnitude. The other variable star that has been of interest over the last year, and those that noted the January sky notes would have seen that David Arditi suggested that Mark Kidger, who was one of the people analysing this early on, suggested that because of the 430-day period, that Betelgeuse might start to fade again in April, perhaps getting down to magnitude 1, obviously not going down as far as it did last time. However, at the moment, at least from the observations we have, Betelgeuse does not seem to be fading. It seems to be holding its line fairly well. But because of these predictions, obviously it would be very useful for people to go out and make observations of it. It's obviously starting to set now into the evening twilight, but to follow it as long as possible, just to see whether or not it does follow this prediction. So Betelgeuse then, or Betelgeuse, is of interest still, and we still don't fully understand exactly what happened. People seem to change their minds every paper that's written as to exactly what happened with that star. Now, another variable star that the BA has been following for well over 100 years now is the long period variable Chi Cygni. And Chi is a relatively consistent star. It has a period that doesn't change that much, and it tends to vary between about magnitude 14 and about magnitude 4.5. So between naked eye visibility and going down a long way. Currently, it approached maximum and is probably now starting to fade again. So it's going to be around 5th to 6th magnitude, but it's a good variable star if you are starting out to try and have a look at. Now, unfortunately, because of the seasons, we can see that this circle here shows where Chi is, but it's in Cygnus, which is now sort of starting to rise in the morning, or at least till it gets to a decent enough altitude that you could make a magnitude estimate that wouldn't be completely moved by atmospheric extinction. So Chi Cygni is something worth going out to have a look at. In terms of comets, we haven't had a huge amount of luck. We were hoping that C2020R4 Atlas would brighten enough to make it a decent run. However, it doesn't really seem to have done it, and these are the current estimates of the magnitudes of these comets from the BA's comet analysis page itself. So R4, as I mentioned, doesn't seem to have brightened as much as perhaps some of us hoped. And on the left there is an image from Peter Carson, and on the right from Francois Google. One of the challenges of this comet is that it has been mostly in the southern hemisphere until now. It's gradually moving north as the seasons progress, but as you can see here from this orbital diagram, here is comet R4. It's moving in this general direction as it's leaving the solar system, and the Earth is moving in this direction. So we should, or potentially could get a decent run at this in the middle of next month. After that, R4 will start to move, sorry, in the middle of April. We're not quite to April yet. So we could get perhaps a better run at that as that moves, but then the comet will move away, the Earth will move away, and it'll start to fade relatively quickly. Don't worry about all the other orbits. This is a track of where it is going to appear in the sky. So this is where it is now. And it's going to obviously track up through Hercules, Boötes, and end up at the end of next month, end of May, sorry, in Leo. But this means again that it's going to be a morning object to follow. It's obviously in Aquila, and then moving up through Hercules. So if you want to have a look at this, you're going to have to get up in the morning. So those people who aren't on a furlough are going to have to either set a remote scope working or miss it that way. The other comet that we had that was of interest was C2021 D1 Swan. And this was first found in the Swan imagery from SOHO. And there was some hope that it might get relatively bright. But again, it hasn't really brightened as much as perhaps hoped. But again, these are some images showing what it looks like at the moment. This one is an evening object, and we can see here where it is now, and it is going to be moving up from Triangulum up in through the end of Perseus and up towards Auriga. So again, this will be tricky because as twilight starts to interfere, you can look out and maybe pick this one up, but it is going to be fading fairly quickly. So people will be of interest. Just something that came out yesterday that I thought I would throw in while we were discussing comets was, as people may be aware, a couple of years ago, we had our second interstellar visitor, which turned out to be a comet and was named 2I Borisov. The image at the bottom there is taken with one of the 8-meter telescopes in Chile. But what has turned out of interest that this comet appears to be one of the most pristine comets ever seen in terms of its evolution. It has a composition fairly similar to Hale-Bopp, but dissimilar to many others. And the suggestion is that because of this, it may have formed in interstellar space and may never have passed the star before the sun. So it hasn't been changed by heating or anything else like that until now. So it's obviously on a long way out now, and I suspect it may even be on amateur imaging anyway. But it's of interest that even now, after a long time after it's passed, we've discovered some interesting facets about that comet. So moving on to the main planets, unfortunately, really only Mars is left, and of course it's fading and getting much smaller. And all the other major planets, as we can see here, are in the early morning sky. So Jupiter's morning, Saturn's morning, Uranus is basically gone now, and Neptune is a morning object as well. And this basically means that they're going to be a bit more difficult to follow. So this is a chart for the middle of next month, and it shows that Mars now is setting quite badly over here, and that is going to make comets a problem, sorry, planets a problem. And this is the morning sky about the same time, at about 4 o'clock. And you can see here that Jupiter and Saturn are extremely low, and they're obviously coming out from their conjunction with the Sun. So it'd be these are going to be tricky to pick up over the next couple of months. And even by the middle of May, we can see that they're still relatively low as the sky is brightening. So this is at 3 o'clock in the morning. So we know that you know, things get worse for astronomers as the summer comes along. So we are going to have a challenge to do that. So planetary observers may struggle a little bit until later in the year when these things come up and look at a higher altitude. So in terms of meteors, well, we've not really had a lot of luck in the next 2 months either. As it says there, the most favorable shower will be the April Lyrids, and they are not a very prolific shower. So you're not going to have a lot of joy on that one. And the only other one is really perhaps more for southern observers, and that's the Eta Aquariids. There are a number of other showers, but unfortunately they only really occur in the daytime, so will be of interest to the radio meteor observers, but not visual observers. I sort of threw this one in. I think we're all probably aware of this now, the Winchcombe meteorite, carbonaceous chondrite, obviously not very strong, as when it hit the driveway, rather than making a crater, it just produced a pile of dust. Not quite sure how you extract all of that, but that's what we get. We were lucky that it was picked up quite quickly, as water quickly damages these things. And this is an image taken by Richard Fleet from Pewsey in Wiltshire of the meteorite on its way through. And we can see that it got very bright, but it exploded and broke up into multiple pieces as it went through. I'm not sure if all the pieces have been recovered, but I'm guessing that people are out there looking for it. it will be interesting to see how quickly pieces start to get into the dealer's hands. But not to be outdone, there was another fireball on March the 20th. Unfortunately, from southern England, it was completely cloudy, something that seems to be all too typical this winter season. But it was seen from Jersey, and sonic booms were heard all along the southern coast. Now, John Mason and Nick James have done their best to try and calibrate where any debris may have fallen, and the current idea is that it could have fallen somewhere in the New Forest area. So if you come across a pony with a headache, then it might be worth checking out where it got that headache from. The New Forest is obviously not going to be a very easy area to pick up anything at all. What is of interest, though, is that this meteorite, whatever its constitution, is likely to be one of much stronger than the Winchcombe one. So particles that would land will probably make little holes rather than sort of end up as a pile of dust on a driveway. The sun, well, unfortunately, the sun still seems to be napping. It hasn't really woken up after coming out of minimum. We can see here that that we're still around 37–40% of the days are spotless. Obviously better than last year when 57% were spotless. But just out of the range of this, at least I assume there'll be another sky notes before that, we have a partial solar eclipse on Thursday the 10th of June at around 10 in the morning. So again, those who are able will be able to have a shot at that. It's going to be an annular eclipse crossing northern Canada, Greenland, and northern Russia. Whether or not we have any BAA members who are going to attempt to get out there and fight the polar bears for a view of the eclipse, I don't know, but I'm guessing we'll hear about it afterwards. The sun hasn't been completely inactive. We've had a bunch of spots running around. There have been a few prominences, and these are images from this month from the solar section's web pages. And today, the sun has nothing showing at all. So we're back to a blank, and it's likely to stay blank for a few days, though there may be a spot around the other side that will come around then if it lasts that long. In terms of the eclipse, this is the map of it from the handbook. So if you want to see more, go and have a look in the handbook itself. And you will see that from southern England, it's going to be about 20%, from northern Scotland, maybe around 32%. So it's not going to be a fantastic job, but it's still something that may prove to be of interest, and maybe by then we'll be able to go out and have a look at it with do some outreach on it, but we'll obviously have to wait and see on that one. So I did say to Alan that Alan mentioned that my main interest is in the deep sky, so I thought that I would at least throw in, just to end the presentation, something about the deep sky. And the title of this slide, The Realm of the Nebulae, not only references back to Hubble, who wrote his famous book called The Realm of the Nebulae, but also this was what the early visual observers, Charles Messier and William Herschel, thought, because as they observed, they found that there was a bigger concentration of nebulae there than there were perhaps in other parts of the sky. And the area that we're really going to look at encompasses the Virgo cluster of galaxies, which is the nearest large cluster to our own local group, something like 54 million light years away. And our own local group is actually part of the Virgo cluster, an outlying group. So as it says there, many of these are binocular objects, so you don't need a camera or a spectrograph. You can just go out and have a look at them. The first person to try and catalogue this area of the sky was a brilliant student at Harvard, Adelaide Ames, and Harvo Shapley, Unfortunately, Adelaide Ames died in a canoe accident at the age of 30, though she would have perhaps done more. And one of the main galaxy catalogues is still the Shapley-Ames catalogue. So she produced a list of galaxies in that area. And those that have been in the BAA a very long time, whether there's any of those on the call or not, will remember back in the late 80s, a young lady called Lee Forbes tried to make a chart of this area based on photographic plates taken by Harold Ridley, who was one of the main BAA imagers or photographers at the time. And this was sort of drawn before we could get easy access to digitized sky surveys, etc. So where is this? Well, the Virgo cluster lies in this area. There's the nebula at that end and Vinda matrix over there, and almost all of the large galaxies in this are in this area here. So this is rising now into the skies. It's quite useful at early evening, so you don't have to stay up late. You can get out there and see what you can find. And the cluster is based around this very large galaxy M87. But you may think it's just one cluster, but in fact it seems to be a dynamically evolving cluster. So there's also a group here based around M84 and M86, and this chain of galaxies here is known as Markarian's chain, after the astronomer that first noticed it. So you can see here that there are a large number of bright galaxies in this area to go out and have a look at. But the main reason for this is to show you this. So this is where our local group is at the middle, and then as we move out here, we can see the Virgo cluster over here. So this is our nearest large group. There's possibly 2,000 to 3,000 galaxies in the Virgo cluster. It has its own catalogue that you can pick up on. But perhaps just to end with, we will have follow-up again on the polarization that was mentioned earlier. So just recently, the M87 black hole team, the EHT team, released another picture of the M87 black hole, but this time in polarized light. So these streaks here, this is light that has been polarized from in the disk, and by seeing that, we can get a very good idea of how strong the magnetic fields are, and perhaps how the jet that we can see coming out of M87 is actually formed. So that's what I have for you this evening. If anybody does have any questions, I would try and answer them. Otherwise, it's very nice for you not to be watching the football. And thank you.
Thanks, Owen, for a great Sky Notes. And we have a comment from Daryl Dobbs, and he'd like to say he very much enjoys your articles in astronomy now, and long may you continue to write them.
Oh, thank you.
And I'm pleased to say we've had 60 to 70 people with us this evening across Zoom and YouTube. We'll also just give it a moment to see if there are any questions. Our next main event is the BAA Winchester webinar on Saturday, the 10th of April. At 2 o'clock, we've got Pete and Paul's Astronomical Challenges of 2021. Then at 3:30, there's the Characterizing of Exoplanet Satellite Mission, CHEOPS, by Dr. David Brown. And then at 7:30 in the evening, we have On an Exoplanet Far and Far Away by Dr. Jesse Christiansen. And I'm not seeing any questions coming. I'll just do a quick check on YouTube. No, nothing there. So once again, oh, hang on, I spoke too soon. From Daryl Dobbs, when is V1405 CAS likely to fade? There's a tricky one.
Well, I think it already is starting to fade. The question will be how quickly it fades. And that will only be determined by continuing to observe it. Novae aren't entirely predictable in terms of what they do. So yes, you'll have to just keep an eye on it and see what it does.
Thanks, Owen. In which case, thanks all, and hope to see you again at